I hope everybody notices and appreciates my new background, very academic. I felt it's more fitting to the highly intellectual conversation that we're leading here. Okay. There's a homework due this week on Wednesday, and that means that on either Wednesday or Thursday, I'm going to give out a new one. So brace yourself. This is where I was last week. We were talking about the one big overarching property that I wanted to discuss for Hamiltonian systems before I go into more specific details. I will also later talk about, even today, stability of equilibria, but we were talking about general properties that help you with a qualitative understanding of Hamiltonian systems. First one was conservation of energy. Second one was conservation of phase space volume. And the third one, although related to the conservation of phase space volume, is still different in nature, which was recurrence, which is a fascinating property of Hamiltonian systems. You cannot expect that for a general dynamical system. What it's all about, was my main take-home message from there, right? So this was a recurrence, and it is true for in the first discussion we had on this. I spelled this out for autonomous Hamiltonian systems. It turns out to extend to periodic Hamiltonians, time periodic Hamiltonian systems as well. And basically, it's about this picture that if you're able to ascertain that your dynamics, the Hamiltonian dynamics, is confined to a compact set of the phase space, so you're able to establish that there's a compact invariant set in the phase space, which I indicate with this wall here. Then any initial, not through any, but if you take an open set, then in any open set, doesn't matter how small it is, there will be initial conditions that return to the same set for arbitrary long times, which is a big deal. I discussed that if I just said, well, at some point they return, the statement would actually be trivial because some actually would never leave if you take short enough times. But here, the big deal here is that for arbitrarily long times, you can give me 2 years and there will be initial condition comes back after 2 years. And then 5 years, 10 years, a gazillion years, there will always be initial conditions coming back over such long time intervals, even though the motion within this set is completely general, right? Now, an extension of that was, which is perhaps even more useful, is that almost all initial conditions return. So this is the typical behavior. Remember, almost all means everything except for a set of measure zero. Measure zero sets are in practice not observable numerically and experimentally anyway, unless you have some special symmetries. So what this actually tells you that the predominant behavior is return. The predominant behavior is recurrence in these systems. What this comes out from is an even more general and very powerful result, which is good to be aware of because it extends this notion of recurrence beyond Hamiltonian systems to systems that can be even odd dimensional as long as they preserve some measure. And that measure can be volume or mass. So you can even apply these ideas to a three-dimensional mass conserving fluid flow, which is nowhere near being Hamiltonian, right? So what that comes from is that the underlying result is Poincaré's recurrence theorem, for which what I stated here is just an application. So this is just an application of the more general result, which is true for maps. If you have a discrete mapping on a finite measure of space, so you have to have some bona fide measure on this space. It can be a probability measure, it can be volume, it can be area, it can be mass, but any kind of mass which is preserved by that map. So this mapping doesn't have to be smooth or anything, but it has to be measure preserving and it has to be invertible. So it has to define a dynamical system in forward time and also in backward time. Should be able to go back uniquely. Then any open set over time will have an intersection with itself. So you pick any open set, which means arbitrarily small, then you will, if you iterate long enough, it will have a self-intersection. And we did a proof of that, right? And then I noted an important extension is that precisely because we have an underlying theorem formulated for maps, one can extend this result to time-dependent Hamiltonian systems that are time periodic, because one can simply pass to their Poincaré map. Okay, And once you pass to the Poincare map, then everything follows immediately. I even noted in a hand-waving fashion that non-smoothness is not a problem either if you have a Hamiltonian system that has impacts and so on, as long as the impacts do not change the phase space volume. So when you switch, say, from one state of the system, so it's a piecewise, say, continuous Hamiltonian system, when you switch from one to the other, and you still keep preserving the same phase space volume, because if you look at the proof of Poincare's recurrence theorem, that's the heart of it, the conservation of that measure. So even through your discontinuities, you got to be measure preserving, same measure always, not just in between, all the way. So even though the impact should preserve the measure. So for instance, you can have perfectly elastic collisions in a wall in a linear oscillator like that have the property. Then, because you still have an invertible mapping when you sample this and you still preserve volume, Poincare's theorem applies and you get recurrence even in systems like this. All right. Any questions on this? If not, what I was promising last time is two kind of what I would consider high profile consequences of this. So these were problems that people were actually discussing. And as you'll see, the point was that the Poincare's recurrence theorem was heavily used in the discussion. So the example one would be is I think in the notes I just call it ideal gas in a partitioned container. I'll just say ideal gas in a container. So the reason is this was a high profile example before I go into it. The story starts with Boltzmann's theorem, which is in, I guess, one of the first major results in statistical mechanics or thermodynamics, whichever way you want to view it. So the Boltzmann, I think it was called H theorem, which is basically one of the axioms in thermodynamics now, is that the entropy of isolated systems grows towards a maximum. So in the absence of external interactions or impacts on a system just by itself, if it's a thermodynamic system, then the disorderliness of the system just keeps increasing. Spontaneously, the system will not converge towards order, an orderly state, but rather it will spread out basically, well, not so spread, but when we talk about gases, it's going to spread, but it basically tends to converge towards disorder in the absence of any external, interaction. And if you have teenage sons, as I do, then you certainly see this theorem in effect. So unless there's an external fatherly interaction, then the disorder will prevail in their rooms. And I think all of us have been guilty of that at some stage in our lives. All right, and this was very well received, but also got people to think about these issues. So I think that this theorem, I have the years here. This is actually in the 1800s, and it has been very inspirational to a lot of people. But also there was resistance to these ideas, and one of the most noted acts of resistance was a counterexample proposed by a mathematician, I believe, a German mathematician, by what's his name, Ernst Zermelo. And this example was also in the 1800s. So the claimed counterexample goes like this, and this is the example I want to discuss. That just imagine that you have a container, and in fact, half of the container is partitioned off at over 2, or the half is not that important. I just want to have some dimensions to talk about it. So this would be a removable partition. And you start out by this experiment by filling up this part with an ideal gas to which the H theorem presumably applies. So if this is an ideal gas, then you have a large number of particles within this part of the container. And just imagine on the other end, you have vacuum. To some degree, you could even, to the extent you can get to perfect vacuum, you can even create this experimentally, right? So since this is an ideal gas, you have perfect collisions, so you don't lose energy. And then therefore, this is the type of system to which the H theorem would apply in general. So then the suggestion was that remove the partition now. And then once you have removed the partition, the current initial configuration of gas, you remove the partition in a split second, the current initial configuration of the gas is very singular because it's not spreading out in the whole domain. From the perspective of the theorem, the entropy is quite low relative to what it could be. So what could it be for this system? Well, the maximal entropy would be reached by this gas now starting to spread out. And at some point, the gas molecules would then evenly spread out this space and may move in some chaotic fashion, but certainly that's what you would expect in an experiment as well. We know that, right? Once you remove a partition like that, you will be able to sense that gas with a sensor anywhere, right? So that's what we expect. So an even spread out is expected, and in fact, it's guaranteed by this theorem, by the H theorem. But of course, that doesn't stop a mathematician from thinking about counterexamples to the intuition based on mathematics, even if it's in apparent contradiction of what you expect physically. So how would you get an apparent contradiction? So let's just look at the dynamical system formed by these. So this is I said ideal case, but what I meant to say ideal gas. So you would have a large number of particles here, the atoms. So n is much larger than 1, right? And somehow we try to describe the system by positions and velocities. From this perspective, this is a conservative system given that the gas is ideal. So the positions can be summed up in a vector q. And if this is a three-dimensional setting, then each particle would have an x coordinate, a y coordinate, and a z coordinate, right? And you have a total of n of these triplets, so x, n, y, and z, n. And therefore, the total position vector in this case would be a 3n-dimensional vector, and it's very large, okay? And corresponding to that, there are velocities that use, so these will be the velocities. And with the help of these, you would then be able to write down a Lagrangian. The collisions with each other and with the walls are perfectly elastic. So one has a potential function, and depending on how you model the collisions, I mean, those might become singular. But the point is that even though you have these collisions, you don't lose energy. So in between, you have just regular conservative interactions in terms of a conservative potential between them. So the Lagrangian L would be the kinetic energy. We're just talking about point masses, so it's a fairly simple form of kinetic energy, minus the elastic potential energy describing, of course, there's various ways of modeling that, but fundamentally it's still a potential, and this is how it would be done if you were to provide a description for this ideal gas in terms of particles. So the TQ dot, we even know its general form, it would be a quadratic form where I feed in all the positions, all the velocities, excuse me, some very big mass matrix, which would normally be just constant times identity, assuming, right, that all the particles are actually of the same size, although that's not important for the argument that Zermelo was making. And this is the potential of elastic interactions. Okay, so this is the setup. We're working in Lagrangian mechanics, so I'd like to pass to the Hamiltonian formulation, which is not hard to do. I mean, the kinetic energy is linear. I'm sorry, it's quadratic. So, and the rest, its VQ is unspecified. But the way you would, the only thing you need to do if you want to pass the Hamiltonian formulation in this context is just add a linear momentum. So the linear momentum, as you might remember, is the derivative of the Lagrangian with respect to the velocities. This is a vector. So that's the same as the derivative of the kinetic energy with respect to the velocities. So you need to take the gradient of this kinetic energy, and that's something we've done before. So this is just mq dot. So you can express q dot as an inverse p. Nothing funny there, and then you just simply plug in this relationship into the kinetic energy, right? So when you do that, you will have two m inverses, one canceling out the other. So you basically will have a Hamiltonian HKQP was 1/2. You see what happens here, right? Then when this m inverse will knock out this m, so I will just get a p, but I will have an m inverse here. So I will have p m inverse p, and this comes this plus. Of course, I normally would have to do a Legendre transform and go through the loops to get to this point, but we had an earlier result that as long as you have a kinetic energy of this kind, then it's always it was the Euler's theorem of homogeneous, positively homogeneous functions. Then you can simply add V of Q. Okay, so we know that. So we do have a Hamiltonian system, and it's a Hamiltonian system. So it starts qualifying for actually, it starts being or starts shaping up as an example for the recurrence relationship. Not that it's immediately clear why that's relevant here, but let's just accept that as an example in that domain now, and let's try to check whether I can apply the recurrence result to this Hamiltonian. So first, to see that in the phase space, which is incredibly high dimensional, because you have a large number of entities here. So what's the phase space like? In this direction, I'm going to show the momenta, and in this direction, say the first position is Q1. And there will be, of course, remaining positions, and I try to line them up along this axis, all of them. So this will be Q2 up to Q3m, and this is just the p vector altogether. So let's try to just have a rough picture of how things look in the phase space. The phase space has some hard bounds in it, some of which are obvious immediately because they come from the geometry. What are the hard bounds? Think back to the geometry here. This was my initial condition, and in this case, all the positions were bounded by k in one direction, and in the other direction by k over 2. So all these had a bound, depending on the direction of k or k over 2. Once I let them out, I mean, sorry, this is supposed to be altogether than a cube, right? Well, that's not what it looks like. But this is the only reason why I had a K there, so that I can talk about the dimensions. Long story short, Q1 can never take a larger value than K, right? That's just the box. So I will also extend that hard bound here in this direction. And it's also true for the others that sort of pictorially, right? Because this is a whole subspace there obeying that bound, no longer just a single coordinate. So this is sort of hand waving to show that these are individually are also bounded by K because they're confined to this box. So in our case, the hairy wall is here for sure, okay? And the Q1, which is the, well, each and every, well, it's not easy to, let me just go on. The P, on the P, I have no a priori bound immediately, but one thing to imagine is what's now the representation of this initial condition that I have shown you here in this phase space. You will have lots of positions, each uniquely labeling one of the particles, right? In this is a huge position vector. And then each and every one of them, when I take a snapshot of this, will have an initial linear momentum. When I put that all together, then in the current phase space, this whole gas configuration, the whole gas configuration is just bounded by, is just represented by a single point, right? So this would be the whole initial configuration of the gas, Q naught, P naught. That whole initial distribution. Clearly, this is an incredibly high dimensional phase space. And then that will be at the moment when you remove the partition and then you let things go. So when you let things go, then from that initial condition, you will be developing a trajectory in that very high dimensional phase space. So imagine that you're starting from here, and you're moving around, and this will be the evolution of the gas. Configuration, just by represented by a single point. And one thing to know that this is a Hamiltonian system, so I know that this would be, which one way or another, confined to an energy surface. And that energy surface is a nice codimension one surface. And as long as I'm not in equilibrium, at any point, which is highly unlikely given that everything is moving, right, in this gas, as long as not everybody is frozen, that will be a manifold. We have proven in general that as long as the energy surface, you're looking at a point which is not an equilibrium point, and locally the energy surface is a nice codimension one manifold. Right. And this is characterized by H of X equals H naught, which would be the initial energy of the gas. Gas upon removal of the partition. Okay. What was X? Well, X is just Q and P is very high dimensional vector. Okay. So let's consider then the following set. I'm going to restrict to an open set of the phase space, the attention to an open set, and I call it S naught. And it will be simply the set of all points in this phase space, which is 3n for the positions, right? And 3n for the velocities, such that when I evaluate the Hamiltonian, it will be less than or equal to the initial energy. Well, I'm not sure if just in a hand-waving fashion, that something to think about is intuitively is below this, right? But it's not quite right. I mean, there will be variations in P and Q. Well, if the energy, it's more like the energy surface is something that is hand waving, right? I don't exactly know how it goes, but certainly this will embrace, it will together with the walls, it will presumably bound, at least it will produce a bounded set. Now, this is not a priori necessarily clear, because even though I have a geometric bound in this direction, I certainly have no bound in that direction, right? So the velocities or the linear momenta can be arbitrarily large, right? So is this the kind of set on which I can expect recurrence? So one thing to note is that I have no problem with the boundedness and the closeness in the Q direction. So the Q are a priori, right, bounded by K. I take here the norm, which is, say, the maximum norm. If individually they are bounded by K, then I would have, you know, if I take this one, then Q norm would be the square root of, if you want that one, of Q, sorry, the norm of Qi squared, right? So those are individual, and I goes from 1 to 3n. So that would be the Euclidean norm of Q. So individually, these terms in the sum are bounded by K squared, because simply I have no way to go beyond the wall of the container. So these are individually K squared. So I will be able to pull out K in the end from the square root. And I have 3n occurrences of those. So the exact constant would be this. Okay, so write it, right. Actually, why don't I use that norm here instead of, because this is the natural norm to use in this context, the length of the vector. So why don't I do that? So this is K3n. N doesn't change once you have agreed on the number of particles. So this is bounded. K is bound, Q is bounded for all times. But like I said, the big question is P. Now, this was the first note. The second note is that when you look at T of P and you add it up to V of Q, that's less than equal to the total energy. Now, the nature of this potential, it's never going to take negative values, right? Because it will have minima at the well, if I compress the spring, then it will have a maximum, right? But the point is that it can actually go to infinity, but I can certainly, it will not go to negative infinity, right? It will be a potential like this. And I can just initialize it in a way so that I can ascertain that T of P is less than or equal to H naught. Now, what T of P is that you have a 1/2 P, I'm sorry, M inverse P quadratic form, which is less than equal to H naught. Since the M is quadratic, so this is like a cup-shaped object, so that will mean that P is also bounded. So it looks like that the energy surface itself, and anything, of course, this is now on the given energy surface, but if I now look for energy surfaces that have even lower energies, and they are even more bounded, so to speak, the Q's obey on any lower energy the same bound, and the calculations that I had here, if then these estimates are equally valid for that, right? Because in lower energy surfaces, the total energy is larger than H naught to begin with. Therefore, the kinetic energy on the lower energy surfaces is also less than H naught. So these are uniform bounds for all the energy surfaces. And I have defined this with a less than or equal sign. And that definition automatically ensures that this set is closed. It's not an open set. So there you go, you have a bounded and closed set, therefore it's compact. But also very importantly, energy is conserved on this particular energy surface, but within S0, there are other energy surfaces. Again, this don't hold me accountable for this. I'm just sort of showing pictorially the other energy surfaces. So you're also confined to those individually. So all in all, this set, which is foliated by this energy, the critical energy surface H equals H0 plus the smaller ones, is foliated by little energy surfaces. So all in all, this is an invariant set. You cannot get out. In other words, once you have your initial energy, it cannot grow because this is a Hamiltonian system. So S0 is compact and invariant. Okay. Now, we have then a Hamiltonian flow on this S0, and any Hamiltonian system, I don't have to write out and check. It's a classic Hamiltonian system. So I just indicate what it is. Generates a volume preserving flow on S0, which I can then sample if I want to apply Poincaré's theorem directly, or I can just refer back to the theorem that I already stated for Hamiltonian dynamical systems that have this property. So this is an example in which I do have a compact set. It is invariant, and there's a Hamiltonian dynamical system defined on it. So like the flow map of which is, automatically invertible, even smooth. Certainly preserves volume. That was volume conservation. So what do I have at the end of the day? I have recurrence on S0. So recurrence does apply. So then what is the big deal? We just sort of we checked this Hamiltonian system. Why is this such a big deal in this example? Well, it's a big deal in this example if you think about the consequences. What does recurrence say? Recurrence says that almost all initial conditions return arbitrarily close to themselves. So I cannot say much about this particular initial configuration that I had for the gas. The recurrence is never as specific as that. For all I know, that can be one of the separatrix trajectories of the pendulum. Remember, that just defied a recurrence. However, what I can say is the following. I can take an arbitrarily small open neighborhood of this. Let's do that. So here. So let's call it U. So this is an arbitrarily small neighborhood of X0. This was the initial gas configuration, X0. And I will see a return to U. So there will be another gas configuration arbitrarily close, that will come back to that neighborhood, and not only once, but infinitely many times. Now, if it's arbitrarily close, right, then think about this configuration here. I can find an arbitrarily close configuration that will come back to itself. So I will find a slightly different but arbitrarily close gas configuration, which will regroup itself, and I can just close the partition again because it's going to be as close as needed to the original one. And the original one was a finite number of points, that therefore it had a minimal distance from the partition. And I can find a gas configuration which is still within that distance, and hence will fully go back. And then I close the partition. And there goes your, apparently, there goes your convergence to a statistical equilibrium where everything is completely spread out. And this is apparently in defiance of the H theorem, because clearly I have returned arbitrarily close to my initial entropy already I had a much larger entropy, right? I was spread out, and I had to decrease the entropy and come back here. That's why this was a counterexample. So the argument goes like this. So there exists arbitrarily close initial gas configuration in this subset U, which I've indicated, that returns over time to the same side of the partition. So this is an apparent counterexample. Well, let's just say apparent contradiction with the H theorem. And this was published, so Boltzmann and others, I think, had to sit down and think about it. Also, one implication immediately is that there will be arbitrarily many returns. And in fact, that's the one that you need to look at, because you could say, all right, you return once, but that doesn't violate any convergence result, right? Maybe you return once and then you go towards the statistical equilibrium completely spread out. But no, the argument is that you will have infinitely many returns for arbitrarily long times. Therefore, you cannot converge to this even spread distribution, because that's no convergence if you at arbitrarily high times you depart. Convergence means that you would then have to stay in an arbitrarily small neighborhood of that completely evenly spread out position, which you're violating with these returns, right? So that's even more important. So that means no convergence to maximal entropy state. So the two things that people have noted as a resolution of this, you can't argue with this, the mathematics is correct, actually. This is true. So the counterexample doesn't involve any mistake. But the way to resolve this is that these return times, if you try to compute them, because there are estimates for them, for this type of a configuration, really for a realistic gas, and taking into account how many particles you would have there, the returns times are multiples of the time of existence for the whole universe, it turns out. Over such timescales, obviously, even the model itself will be no good, because all the assumptions you make about idealization will just break down. But even if it was good, because in principle Boltzmann theorem would cover it, these are very unique initial conditions that do that, they say, or not so much unique initial conditions, because recurrence is in fact generic in Hamiltonian systems. But when you take a particular snapshot, okay, then at any finite time, then these will be so rare, and that the recurrence will be at any finite time practically unobservable. Still, you could say, yeah, right, but I mean, they do return. So for me, a better argument against this, which is also sort of brings out more of the mathematics, is the following. If you actually look at the statement of the H theorem, it is only valid in the perfect thermodynamic limit, perfect. And the perfect thermodynamic limit with this model is only reached if you actually take the number of particles to infinity, okay? And if you take the number of particles to infinity, then even though you might think of this box as a unit box, you are in an infinite dimensional phase space, and anything like the unit ball in an infinite dimensional phase space is no longer compact. So if you have a unit ball, which is like this, so you have a closed and bounded set in infinite dimensions, because these arguments would work there as well, it doesn't imply the same type of behavior that you would have on compact sets in finite dimensions. In infinite dimensions, you can keep exploring new and new directions continually. You never run out of new directions. So like this famous result is that the unit ball is not compact in an infinite dimensional phase space. So that's the one I would prefer to shoot this down, but it certainly got people to think. So the other thing is that the H theorem assumes perfect thermodynamic limit as n goes to infinity. But then the phase space is no longer compact. Phase space is infinite dimensional, rather. It's not compact in finite dimensions either, the phase space. Closed and bounded sets are not compact. So what is the particular implication of that? Well, if you have say you have return times, a function of which would be your return time in a finite dimensional case, and the return time is a distribution on a sphere, and so somehow you can show that it's continuous, which is it? No, it's not going to be continuous because it's not even defined for some cases. So let's forget the return time, but can take just any reasonable function that is your observable for the motion. Then in a finite dimensional space, on a compact sub, on a closed and bounded set, it will have a minimum and a maximum. In an infinite dimensional space, no. You don't, if it's even on the unit sphere. So that was an interesting example. Any questions on this one? And I have another one in store.
Yeah, maybe just a quick one, if I may. Am I audible?
Yeah.
Yeah. I was just wondering, how would the model change if we introduce some dissipation into it? So I'd wager it would rather stop in a more spread out fashion because it wouldn't have the energy then to go back down, maybe, or are there any intuitions this way? No?
So unfortunately, the minute you have dissipation, the system is no longer Hamiltonian. The flow map is no longer conserving area. So then not quite, right? One would have to have very specific considerations about the model that I know. But unfortunately, all these statements are out the window once you switch to dissipative systems. Anybody else? So example 2, this was another famous thing, but it was almost 100 years later. So it goes by the name of Fermi-Ulam-Pasta experiment. Or FPU or FUP. It even has an acronym because it's been referred to so many times. So it was 1955, after the Second World War, and these were numerical experiments that these famous physicists were conducting in Los Alamos. You know, only very few places had supercomputers or large computers. Let's call them large computers by today's standards, right? And this is the first time, as far as I know, that a physical theory was checked by numerical simulation. And that was 1955, the first time, something that we now do on a daily level. Whenever you have an idea, right, you go ahead, simulate it and check it out, right? That was the first time that people just simply were not sure about the answer, and they used a computer to check their theories. So what was this? This was, again, so first numerical, I think it's just good to know anyway that this is the first numerical experiment to check a theory. And it was about weakly nonlinear oscillators. Which are clearly a model for a lot of things. So if you have just linear, the linear limit, so to speak, when you have no nonlinearity, then they can be described by a Hamiltonian system, which physicists would write down immediately, you know, without necessarily having a particular system in mind. They just think about a Hamiltonian, which would be 1/2 times, you see, the kinetic energy plus the potential energy, but the potential energy would be the potential energy of a linear oscillator. So, you know, in theoretical chemistry and theoretical physics, people just write down these models with a bit of this form. So pi squared over mi, right? That's the type of quadratic kinetic energy that we have just seen, and plus the corresponding oscillator part, which would be omega I squared, the natural frequency of the oscillator, times qi squared. So I goes from 1 to n. There's just many, many linear oscillators. So you write out the individual Hamiltonians, right? Then they go like this: qi dot equals pi over mi, okay? And pi dot equals minus omega I squared qi. This is your good old harmonic oscillator. If you then, you could see that by taking the second derivative of qi dot, and then you recover the harmonic oscillator as we know it. Hopefully, let's see, did I get this right? Pi mi, and I'm just hesitating about the mass, because I think this is already mass normalized. That's where you get natural frequency. I think so. I think this is okay. If not, then still the same. It's the same structure for the Hamiltonian. What's particular about these is that we have decoupling linear oscillators. So the energy of each and every mode is just constant over time. We know that because these are individual harmonic oscillators. So you have n decoupled harmonic oscillators. So this is the time, and these are the individual modal energies. Then each and every energy would be whatever it was at the beginning. Like so. So this would be E1, E2, and this is E capital N, dot, 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 right? So if you were to check their energy in between, then you will always get the same line, because these oscillators do not interact with each other. So what were they interested in? They had a hypothesis that if you have the weak nonlinear coupling, then as long as that's a generic type of coupling, so this was, so if this was H naught, let's say, then this is H equals H naught plus H1, and where H1 is just some sort of, so it will be small, okay? And some sort of coupling that involves all the oscillators, not the velocities, but their positions at least. Okay, so all of a sudden, it's not individual linear oscillators just doing their thing, but there would be nonlinear geometric couplings between adjacent ones, or potentially not just adjacent ones, but other ones, right? And all of a sudden, this is more like a realistic beam. For instance, the model for for a beam, which is just sort of oscillating by itself, right? With many, many degrees of freedom, couplings are not through velocities. Then from all sorts of statistical reasoning, the prevailing view in physics was that you have equipartition of energy. So in other words, if you do start with an initial condition that might be assigning modal energies like that, then even though that was your initial condition, once you turn on the perturbation, then the large ones will start decaying and do their thing, and then these will increase and do, and the prevailing view was that here you have some general statistically stationary chaotic behavior. And this was set up for a large number of oscillators, the first simulation. And these are the names of the physicists, and things were going very well at the beginning. So they were, very soon, they were getting the patterns that they wanted. And, these sort of oscillations, okay? And somewhere in the middle. Equipartition too, right? So these oscillators should be identical. Why don't I do that? So mi equals m. So they are like, identical oscillators. So you sort of, especially if these are very different, then you kind of want something in the middle, right? And then, yeah, there will be variations there, but something in the middle. So initial experiments do actually confirm this. So they were very happy to see this. They finally got, their time on the machine, which was a very cherished opportunity there. Of course, these are big names. Fermi, mind you, was among them. And then, they were just doing, all right, so what if we try this? What if we try that? Just to make sure you document it well. And things were going well until one night, the word has it, they forgot to turn off the computer. So the computer was running longer than the previous runs. So much to their dismay, when they came in next morning and looked at the numbers, they were seeing solutions coming back very close to what they were starting from, and it was totally unexpected. So the energy would run out from this mode, right? And then during the day they would do this, but they left it running long enough, and all of a sudden they could see outcomes that it was coming back there. That was totally against what they were expecting. If you run an actual simulation, just before the class, I was trying to copy, which sort of just a little demo of this, but oops. So it's more like this, exaggerated a bit. This is an actual simulation, not from their experiment, obviously. It's just a reproduction, even just for 3 oscillators, not for a whole lot. When you do this for 3 oscillators, you will see this type of recurrence earlier, but when you do a lot, then it will take longer. So here's the thing, right? This was the initial energy, and the other 2 had 0 energy. So one of the 3 modes just loses that energy very quickly. The others gain energy, and then you have these oscillations. This is even more striking when you have a large number of these oscillators. Okay, you just initialize, then this even goes on for a long time, but inevitably, look at what happens here. Against all odds, against all thinking, this dominant mode is regaining energy. And then accordingly, because total energy is conserved, these are starting to lose energy, okay? And of course, you will not necessarily go back to the same point in time, but what they noticed once they started noticing this, they actually started doing longer and longer runs, then they noticed that the more they wait, the closer they get back to the initial configuration, okay? Which was against their intuition, until then, I guess, they started thinking more in more analytic terms about this, because the prevalent view was back then is just statistical mechanics, statistical physics, right? Everything is governed by probabilities, so on. But after all, these are very deterministic systems. So did I write the initially confirm this, but longer runs, which were accidental initially. Revealed closer and closer returns. To the initial energy configuration. So it seems like a recurrence phenomenon, but does that really follow from what we have seen? So we certainly have a Hamiltonian system, right? That's so is this explained by recurrence? That's the question. Poincaré's recurrence. So we have a Hamiltonian system that no question. So if we want to apply any sort of reasoning to the flow map or a Poincaré map, which we sample, this is an autonomous system, so we can sample at any frequency. So the volume preservation is okay, for sure. Excuse me. And also, whether or not we apply it to a Poincaré map or to the flow map, it will be invertible. So that's not the question. The question is really whether we can state that this whole dynamics is taking place in a compact subset of the phase space. Okay, can we state that? So the observation for that is that the Hamiltonian is positive definite at the origin. Why? Well, the Hessian of the Hamiltonian is whatever it was before perturbation. So if you take the second derivatives, it will be something like 1 over m1, for the masses. When I take second derivatives, there's no cross derivatives. Oh, these are the p second derivatives, and it clears out the p dependence. And then you have the omegas. So you have omega 1 squared down to omega n squared, and everything else is 0. So this was what happened before I added the perturbation. Now, whatever the perturbation is, that's just order epsilon, right? So if these were order 1 numbers and I keep the nonlinearity weak, then that's not going to change matters all that much. Plus the type of, I want to keep this an oscillator. So what I want to write out here, which I didn't do, is that I still want to keep, they did keep, these will be still oscillators. So that means that the contribution, the df, I didn't write it here. So the df at 0 should be 0, right? So when I calculate the Hamiltonian contribution from the nonlinearities, then at the equilibrium point, they should still preserve the equilibrium point, because the gradient of the Hamiltonian should be 0 at the equilibrium point. That's just to say that these are really bona fide oscillators, right? That they do not create some other motion that would completely pull you. These are still oscillators. This was the subject of this experiment. But other than that, they're completely general, right? So if that is the case, that means this is positive definite. There's no negative eigenvalues there, right? So now remember the Morse lemma. I basically told you that if you have a critical point, which this function does have, the full Hamiltonian, because the full Hamiltonian, based on my assumptions, vanishes. The gradient of that vanishes at the fixed point. At any Hamiltonian fixed point, right? This is the full Hamiltonian. The Hamiltonian would have a critical point. because the only way, since J is non-degenerate, the only way for this right-hand side to vanish is that the grad of H must be 0. So therefore, by definition, the equilibrium point is a critical point for the Hamiltonian always. Okay, and then since and this is taken at 0, and since this is positive definite, okay, then remember the Morse lemma guarantees that I can always locally introduce coordinates such that these are, let's call them y, and they're also taken from this, that their dimensionality is just the same, such that in the new coordinates, I can rewrite the Hamiltonian. So, all right, let's just, y is equal to, what do I write this? Let's just write x is a function h of y. So I rewrite the original Hamiltonian, which is h of x. I write h of little h of y, right? So which is just the Hamiltonian written in the new coordinates as y1 squared plus y2 squared, blah, 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 up to y2n squared, because that was the statement that, you know, you calculate the number of positive eigenvalues for the Hessian, which is n, 2n, sorry. So then you include 2n of the coordinates just with one coefficient, and then you start taking the negative ones minus multipliers of some of the y's corresponding to the negative eigenvalues that you would have from the Hessian, but the Hessian has no negative eigenvalues. So this is the local representation. So that tells you that no matter what you put down here in terms of detail, as long as it's a weak nonlinearity, this is the shape of any energy surface near the origin. So the energy surfaces are spheres. Also remember that then by the foliation theorem, that's why if you do not introduce any other equilibrium point, which, so in the absence of other equilibria, all energy surfaces are spherical globally. So as you move away from the single equilibrium point that you would have for such an, you know, when you have an oscillator system, you start pushing them away from the equilibrium position. If these are really oscillators, then they will not like staying in the perturbed position because you're stretching some of the strings, right? If this is really a gigantic oscillator system, you will not have no other equilibrium position. So what happens here is that all the energy surfaces up to a diffeomorphism, they're not going to be exactly spheres, right? So with some exaggeration, they might look like this. You have H equals H naught. So if you then define any region here to be S naught, which is the, again, the set of points in R2n. Now I'm writing it in the original coordinates. I will establish the topology of the energy surfaces in the Morse lemma coordinates. But once I know their topology, I can picture them in the original coordinates. They are taken back to that set of coordinates by this diffeomorphism, change of coordinates, such that h of x is less than or equal to h naught. So this is a compact and invariant. So each and every motion, depending on the initial energy, I can confine each and every motion to a set which is compact invariant and also has non-zero measure. That was important. I didn't say that in this application here in the previous one, right? So it's not just that codimension one surface on which I have this result, but it's something that has finite volume, which was an assumption going into the recurrence theorem. It has to be of finite volume. Then what do I conclude again? Almost all initial conditions come back arbitrarily close, right? But unlike in the previous example where those return times were exceedingly long because the number of potential configurations was so large, because the number of particles was so large, here this was a smaller number of particles, so you didn't have to wait that long, right? So that's an explanation. So this is something that even, you know, very high profile even Nobel laureates might overlook. But if you know the basics of Hamiltonian systems, you can save yourself a large-scale physical computer experiment and computer time, and you can know in advance what the result would be, which they overlooked. So this explains the observed recurrence, which they, I guess, realized afterwards, after they got duly surprised, right, by seeing these patterns. And then I said, okay, wait a second, we can explain this. I don't know actually if it was any of these physicists who explained it, but certainly this has entered the literature as a spectacular example of, had I known it before, had I thought of the Poincare recurrence theorem before, I would have known the answer. Good. Any questions on this? I'm done with the recurrence discussion. And I'd like to still spend some time on Hamiltonian systems, or more sort of even more practical aspects. So this was conservation of energy, conservation of volume. Remember, conservation of energy applies only when you have an autonomous Hamiltonian system. Conservation of volume applies always, and recurrence applies when somehow you can pull in the application of Poincare's recurrence theorem. The cleanest case is when you have either an autonomous Hamiltonian system or you have a time periodic Hamiltonian system. In both cases, you can easily pass to a map to which you can apply the recurrence. So now these were the general properties. Now, still, these are good to know, but when you actually start building your knowledge or understanding of a particular Hamiltonian system, what can you do? Can you still also profit from the mundane things that you would do, which is stability of equilibria and then moving away from equilibria? Are there further goodies in the Hamiltonian toolkit that you can rely on? So the next one would be of stability of equilibria in Hamiltonian systems. Points. Okay. And again, these are important. A lot of the models, I mean, we like to say that real systems are dissipated, right? And which it is true, but some of the systems that people encounter, say in theoretical chemistry, it's unclear where even dissipation would come from. So you look at any molecular dynamicists, they will be using Hamiltonian systems. If you look at the state-of-the-art simulations of the solar system, because people would like to understand where it evolves over millions of years, Hamiltonian systems, okay? Because basically dissipation doesn't really play a role there, right? Or if you just look at, you know, in lower dimensions, fluid mechanics, two-dimensional fluid flows, since they are incompressible, preserve area, they do have a stream function. You can have two-dimensional turbulence, still a Hamiltonian system for the particle motion, right? That's, by the way, a confusion that I've seen that in the fluids community. They say, oh, turbulence is a fundamentally dissipated process, they say, which is true in the phase space of the governing equations, which are the Navier-Stokes equations. So when you look at the Navier-Stokes equation in their infinite dimensional phase space, that's a dissipative system. You have viscosity, but the output is the velocity field is incompressible. So the incompressible, when you do particle simulations in a two-dimensional fluid flow governed by a stream function, those are always Hamiltonian, even if it's the underlying velocity field is turbulent. And I've seen this argument made by experts in fluids who didn't really think about this carefully, that, you cannot have a Hamiltonian description for particle dynamics, not for and claim that you're simulating two-dimensional turbulence, because the Hamiltonian system is conservative, and we all know that turbulence is dissipative. See the disconnect between, and one has to really then be careful and clarify at what level fluid flows are dissipative and at what level are they conservative. Again, three-dimensional fluid flow, it can be three-dimensional turbulence, no longer Hamiltonian, but the particle motion itself in an incompressible mass-conserving flow is a measure-preserving flow. So for instance, if you're able to confine it to a three-dimensional box, you have the recurrence theorem applying immediately, even though that velocity field was generated by a dissipative dynamical system, which is the Navier-Stokes equation. Good. So stability of Hamiltonian fixed points. The very first thing is something that follows from what we have already seen. So if I set up the problem like this, x dot equals j dhx, x is going to be 2n dimensional. Okay, j is just this usual 0, I minus I. I is the identity in Rn n by n. Okay, so the system is autonomous. Because in non-autonomous systems, you in fact do not generally expect fixed point to begin with, right? Unless you have some symmetry in the system. So the system is autonomous. And the first observation, and oh yeah, sorry, I knew I was forgetting something. You do assume that you have an equilibrium point. So, and that can be at, I guess, at some x naught. That just means that x naught is a critical point of the Hamiltonian. So x naught is a fixed point. So if x naught is a fixed point, then you always have this relationship that's a critical point for the Hamiltonian. That kind of the first order basic observation is something that already follows from what we have seen. What is the first question you ask about the fixed point? Stability. A fixed point by itself is uninteresting because it's not observable ever, right? It has measure 0, it's a single point. It's only of interest to us in as much it has always an impact on nearby points. So it's really the stability of the fixed point that matters. One thing about Hamiltonian stability is that the Hamiltonian fixed point is never asymptotically stable, okay? And that falls under the general umbrella of the statement that I made before, is that the Hamiltonian fixed point, if it was asymptotically stable, it would be the simplest example for an attractor. And there's no attractor in Hamiltonian systems, because that would imply that the domain of attraction shrinks onto that attractor, whatever that is, so you would not conserve the volume in phase space. This is a particular example of an attractor, the simplest one. It would mean that you have a neighborhood that shrinks down to the point if it's asymptotically stable, and that cannot be in a Hamiltonian system. So x naught cannot be asymptotically stable. Reason is, see earlier observation about no attractor in a Hamiltonian system. Right, so this was kind of the simple-minded picture that you imagine that you sort of had domain of attraction. That would mean for x naught that you can define a ball around x naught of initial conditions, perhaps tiny, but you would have a B delta ball. So first of all, it has to be stable. And certainly I'm not saying that it cannot be stable. It can easily be stable, and if you have stability, excuse me, you're certainly able to confine all trajectories, initial conditions, not trajectories for all times, to the interior of a ball. But if you look at the definition of asymptotic stability, it also means that not only is it stable, but you also converge to the fixed point over time. That's what the domain of asymptotic stability is. So it means that you can set an arbitrarily much smaller ball here. So, B tilde, and over long enough times, the B delta will be in the B tilde. I'm not going to write the details of the argument. You already have, the notes have a bit more, just at a hand waving level. All trajectories starting on B delta will enter that smaller ball in some time. They have to, because they are converging to the fixed point, all of them, no exceptions, okay? And they are converging, so they will then, for a small enough ball, they will not leave it when you wait long enough. So for each and every trajectory, you can wait here long enough so that it enters that little ball for good. There's a time for that, okay? Now, here comes the continuity of the flow map. So that time will be a continuous function. You can select it to be a continuous function on this ball. If it's a continuous function on that ball, then it will have a maximum on that ball, which just means that if you wait long enough, then by that time, everybody on the outer sphere must have entered the lower sphere. And then you see the issue with that, because the two spheres clearly have different volumes. And that would mean that if you have waited long enough, then the flow map would have mapped that larger sphere into the smaller sphere, and that would violate the conservation of volume. Okay, so F T naught T applied to B delta B tilde would violate conservation of volume. Okay, so what can you have then? This is the sort of the general statement. And let's look into that more. So then you say, okay, I try to be then more specific about the stability. I know that I cannot have asymptotically stable equilibrium point, but I can still have stable ones, and I can still have unstable ones, and I'd love to know which one I actually have in a given system. So then that brings you to the study of linear stability first. When you look at linear stability of an equilibrium point, the first thing you also always do is linearize. So what do? You take the Jacobian of this Hamiltonian, evaluate the Jacobian at the fixed point, and you will use that as a coefficient matrix for the associated linear system, for which we used y, x minus x naught, and this is the linearization, which is the leading order dynamics in this y. I can hop over J when I take the Jacobian of this, right? J is constant, so I can just hop over there. And at that point, I will be taking the Hessian of H at that point, x naught, and then multiply by y. So this is the linearized Hamiltonian system always. I can also write the linearized Hamiltonian system in a compact form, luckily, like that. And not only that, but also if you stare at this long enough, or maybe not that long enough, you all of a sudden realize that maybe this is also a Hamiltonian system, which wouldn't be a bad thing to have, given that all these Hamiltonian systems have nice properties. So maybe I can use that. And indeed, it is a Hamiltonian system. So this is also Hamiltonian. With the Hamiltonian, which I call H tilde, which is 1/2 the inner product of y with the Hessian of the Hamiltonian and x naught y. And if you work this out, the gradient of this Hamiltonian, I don't know how well this is readable. So x naught y. So the gradient of this Hamiltonian is just first you hit differentiation here and there, but because of the symmetry, this is a symmetric matrix. You can always put it on the other side. So all in all, you get the same result from both. So that will be just the Hessian times y. And then you get the, when you then create a Hamiltonian system out of this with the same canonical matrix J. And this is what you need to write, and that's exactly the same Hamiltonian that we had here, right? So this is also a Hamiltonian system. So one implication of that the linear is also a Hamiltonian system, right? That the divergence of the right-hand side is 0, for instance. We've done that calculation. So what's the divergence of the right-hand side? So the divergence of the right-hand side so the divergence of, what's the right-hand side? J d squared h x naught y. Divergence now, taken with respect to y. That's just the trace of the gradient. So if I take the gradient of this now with respect to y, then it just simply, the Jacobian with respect to y, then it simply takes out y, and I'm left with this matrix there. So I need to take the trace of j d squared h x naught. And that's a calculation we already did before, so I'm not going to repeat it. Just you can write down as the matrix of matrices and figure out that this is 0. Okay. So that's just rewriting what we knew to begin with. But also, if you stare at this, then this is just a coefficient matrix of the right-hand side. So you will be always dealing with linearized Hamiltonian systems whose coefficient matrix has 0 trace. So this is the trace of the coefficient matrix of the linearized Hamiltonian. So if the trace of the matrix, whose eigenvalues now you will duly calculate for linearized stability, is 0, then you immediately know something about the eigenvalues, namely, no matter what, in a Hamiltonian system, the eigenvalues will always add up to 0. That is not something you have for a general system. So again, somebody presents you with a numerical calculation for the stability of the Hamiltonian, something related. They must add up to 0 modulo machine precision. Otherwise, there's something wrong there, right? So that's already important information to begin with. There's something that's not immediately obvious, but that will be a homework problem because it's still not hard to show. In addition, you have a further symmetry property. So this is a homework problem. What also turns out that if lambda, which is generally speaking a complex eigenvalue, of this linearized system of star, then so is minus lambda. And this is new, right? Because this doesn't follow from anything we've seen before. It's a nice property of Hamiltonian systems. So first you knew that if lambda is an eigenvalue, then lambda bar, which is the complex conjugate, is also an eigenvalue. You also knew that the eigenvalues have to add up to 0. That's already 2 things. And the third thing is that if you have an eigenvalue, which is anything, a complex number, then its negative must be an eigenvalue as well. So then the possible eigenvalue configurations, without doing anything, must conform to the following picture. So in the complex plane, that's not how I wanted this line to look. Okay, that's better. So this is the complex plane. So the real part of lambda I, lambda j, so that not to be mistaken for the imaginary unit. You could have, first of all, nothing stops you from just having all zeros, right? Except that you will have to have an even number of zeros because it's an even dimensional system. So if you're 2n dimensional Hamiltonian system, then you will have to have 2n real zeros. But that also nothing stops you from, once you have a real eigenvalue, okay, then having a complex conjugate also an eigenvalue is not saying much because it's just the same eigenvalue, but having to have the negative of that already tells you something. So that's a constraint. You just cannot have one on one side and on the other. Okay. If you have one eigenvalue here, then you know anyway that the complex conjugate has to be an eigenvalue. So in this case, the negativity of the eigenvalue is not giving you extra information, but in this case, it is giving you extra information. So they have to occur on pairs that are symmetric with respect to the line. More than that, if you have now an eigenvalue, say here, somewhere here. Is that possible? Well, let's see. Certainly, the complex conjugate has to be, for any dynamical system, an eigenvalue. But more than that, in this case, you reflect this with respect to 0, and that has to be an eigenvalue as well. So before you know it, although I'm not doing justice to the symmetry of this, but one such eigenvalue like this, immediately, if you know that one line that exists, you immediately know 4 eigenvalues, all right? So that's really good to know. So just any one of these, immediately there will be a symmetry in this direction, and there will be a symmetry in this direction. One of them is by default for any dynamical system. The other one is the consequence of the fact that if this is an eigenvalue, the negative of that is also an eigenvalue. But then this is a complex number, so its complex conjugate must be an eigenvalue as well, right? So there are 2 steps involved here. Okay, so this is always the case. And just think about what this means. It means that you have positive and negative real parts corresponding to spiraling here, inwards and outwards. So on this subspace, on the corresponding eigenspace, you actually see something like this. A spiral outward, which we think of as characteristically dissipative, right? And yet it can happen in a Hamiltonian dynamical system, because the reason for that is that there will be another eigenspace automatically here in the phase space on which you have just the opposite, because these have negative real parts. So they are spirals inwards. So this can easily happen in a Hamiltonian system, even though it cannot be asymptotically stable, it's not dissipative, but you will find subspaces already for linear Hamiltonian systems on which you see characteristically dissipative dynamics, okay? And this is sometimes hard to digest for the first time you see it. And I have to confess, so I had a student project when I was a master's student, and I wrote a paper about this, and then I submitted it, and it was already reviewed and I think accepted. And then I gave a talk about this at the math department where I was an undergraduate, and some professor who I respected very much at the math department, when I presented the results that I had, doesn't matter the context, it involved eigenvalues like this. And he said, no, this cannot be right. And I said, why? And I got very nervous because I have a lot of respect for the person. He says, Hamiltonian systems cannot show spirals. So that is wrong. So immediately, without thinking too much, I immediately wrote an email or letter. I forgot, oh, probably there was no email that back then there, but a letter or something that, sorry, I made a mistake. I'm withdrawing the paper. It's wrong. And then I still haven't, and on the same day, on the next day on the bus, I was still thinking, wait a second, what are the basic constraints that we have on Hamiltonian systems? Do I know a basic property that says that I cannot see this in a Hamiltonian system? Well, in a planar Hamiltonian system, surely, because that would violate conservation of volume. But we are now in a higher dimensional system. You might be shrinking volume in this direction. It's expanding in the other direction, right? So then I wrote another a letter that, sorry, actually, that was no problem, forget it, right? And it did go through, right? But if you don't see these before and you're just working with very low dimensional systems and you have this picture about dissipative systems in your mind, then you might easily get confused. This actually can happen in a Hamiltonian system. Good. Overall phase space volume has to be conserved still. Questions, if any? So at least you know if you present your master's work and it involves Hamiltonian systems and somebody says that this cannot be right, then you might remember my story and you say, nah, it can. I've heard this before. But interesting, just to let you know, there were other people sitting there. It's like a bunch of 10 other people, right? And they all said, yeah, right. So clearly, I don't even think I had my master's degree. Maybe I just got it, right? But certainly, I immediately gave it to Oka. I made a mistake. But having said that, this also shows that that's why you have to. I certainly didn't have a course, had not had a course on Hamiltonian systems, right? This was already, high-level study, as it is still, unfortunately, in most places, right? So these are good to know in advance, and because then the classic example of knowing in advance what you can and what you cannot get. So self-consistency check.
Just a quick one.
Yeah.
Did this still happen in Hungary, or?
Yeah, it did.
Yeah,
yeah, but it's not. You wouldn't know the people who are.
Okay.
And it doesn't reflect badly on them because they were very competent. I'm just saying, it just shows the value of just knowing certain things that they had not known or not thought about, right? Okay. Anybody else? Okay. Thanks for your attention. We'll continue with this tomorrow. Just there's more really interesting things in the area of stability of Hamiltonian systems. This was actually a big subject a long time ago. And the main thing that really got people concerned, I don't know, concerned, but at least interested, the fundamental question if is the stability of the solar system. And the solar system is, but to a very good approximation, a Hamiltonian system. Things are moving around, but once you factor out certain symmetries, then in the remaining set of coordinates, the solar system can be thought of as being, or at least a few body problems can be thought of being in equilibrium. And the question is, after you have factored out some of the rotations, the question is that configuration stable or not? So there's been a long-standing interest in the stability of multi-body problems, which are all Hamiltonian. That's why I'll give you some results related to that.
Just a maybe very naive question. Doesn't it violate volume preservation, or
what?
The solar system.
The solar system violate volume preservation. So it's a very good point. Volume is preserved where you would not see, because it's not the physical volume, right?
Okay.
It's the volume in phase space. Not in space, but in phase space, right? In the position and momentum variables. But when you talk about stability, you will have to work in that space, right? Because not only can you think of positional perturbations to your equilibrium, but also velocity perturbations, and the two together define stability in that space. But it's a very good point. A little bit related to these pictures, right? Because you see, I mean, not entirely, because these subspaces turn out to be symplectic, so which means that they actually are little positions and and momenta by themselves, right? So this, so it wouldn't be just entirely positions when you see this spiral here. And it would be always a mixture of sort of some generalized position and generalized momentum anyway. But that's a good point. That's, one has to remember that this is in the phase space, not in the physical space. Right. Anything else? If not, then see you tomorrow. Have a good evening.